Welcome to The Explainer. Today, we're pulling back the curtain on the magic that powers our digital world. Have you ever really stopped to think about it? How could millions of people be streaming movies or searching the web at the exact same second without the whole thing crashing? Well, the answer is all about something called system design. It's the invisible blueprint for these massive applications.
Okay, that sounds a little textbooky, right? So what does it actually mean? It just means making a bunch of smart, deliberate choices so that the systems you build are scalable, reliable, and efficient. This isn't just about acing a technical interview. It's about building software that can actually handle the chaos of the real world.
So, here's our game plan. We're going to walk through the foundational pillars that hold up pretty much every big digital service you use every day. We'll start with how they talk, where they store stuff, how they grow, and how they stay fast. Let's do it.
All right, first up, networking. You gotta have this. It's basically the plumbing of the internet, the thing that governs how all the different parts of a system talk to each other, and, more importantly, how they talk to you.
At the very heart of it all is this thing called the TCP/IP model. It's a 4-layer stack that handles everything. Think of it like sending a package. The application layer, that's you writing the letter. The transport layer puts it in an envelope. The internet layer is the postal service figuring out the route. And the network access layer, that's the actual mail truck hitting the road.
And inside that transport layer, you've got this really interesting choice to make. You've got TCP, which is like sending a certified letter. It's a bit slower, but you get a confirmation that every single piece arrived in the right order. Perfect for an email. Then you have UDP, which is more like throwing a bunch of postcards. It's super fast, but you don't really know if they all get there. And for video streaming or gaming, that's a trade-off you're willing to make for speed. So how does your computer find anything? When you type in a website, say google.com, it kicks off this amazing journey called a DNS lookup. It's basically a global phone book for the internet. Your computer asks a server, which asks another server, which asks another one, getting more and more specific, until it finally finds the exact number, the IP address it needs to connect. It happens in milliseconds. It's just incredible. Now, you've probably heard of proxies. They're just middlemen, but the key thing to remember is who they're working for. A forward proxy works for you, the client. It sits in front of you and hides your identity from the internet. A reverse proxy, on the other hand, works for the servers. It sits in front of them, protecting them, balancing the traffic, and just generally making their lives easier.
And CDNs? CDNs are what make the modern web feel so fast. Let's say you're in London, and the video you want to watch is on a server in California. Instead of your request traveling all the way across the ocean, a CDN has a copy of that video on a server right there in London. It cuts the travel time down to almost nothing. And poof, your video loads instantly.
Okay, so all this information is flying around, but where do we actually put it all? That brings us to the database, the system's brain, its long-term memory.
And right away, you've got a huge choice to make. You can go with the relational database, or SQL. Think of this like a perfectly organized spreadsheet with strict rules and columns. Everything has its place. Or you can go with NoSQL, which is more like a file cabinet full of flexible documents. It's awesome for data that's messy and doesn't fit neatly into a table.
And yeah, NoSQL isn't just one thing. It's a whole family of databases. You got different types, and each one is a specialized tool for a specific job. You've got key value stores for super fast lookups, and you've got graph databases that are perfect for mapping out complex relationships, like in a social network.
This highlights one of the most fundamental trade-offs. ACID, which you usually get with SQL, is all about reliability. Think of a bank transfer. It has to be perfect or it doesn't happen at all. Base, which you find in NoSQL, prioritizes availability. It says, you know what, it's more important that the system stays online. Even if the data is a little inconsistent for a few seconds, it'll all get sorted out eventually.
You never want to keep all your eggs in one basket, right? It's the same with data. To make sure we don't lose everything if one server fails, we use replication. It just means we keep identical, live copies of our database on a bunch of different machines. Simple, but absolutely critical.
Okay, so your service is a huge hit. Awesome. But now, what happens when 1 million people show up at your digital front door? You need to scale. And this is all about planning for that success from the very beginning.
You've basically got 2 ways to grow. You can scale up, which is like taking one car and putting a bigger, faster engine in it. It's easier, but eventually you just can't make the car any bigger. Or you can scale out, which is just adding more cars to the road. It's more complex to manage, but you can add cars forever.
Almost every huge service you can think of uses horizontal scaling.
The famous CAP theorem. It's basically the you can't have it all rule of system design. It says in a real-world system where network connections can fail, which is always, you have to pick 2 out of 3: consistency, availability, and partition tolerance. You can't have all 3 at the same time. You must choose what to sacrifice when things go wrong.
So, how do you actually achieve this kind of massive horizontal scale? Well, the modern answer is often microservices. Instead of building one giant monolithic application, you break it up into dozens of tiny independent services. Think about Netflix again. The login system is one service, recommendations are another, video streaming is a third. They can all be managed, updated, and scaled completely separately.
All right, last big piece of the puzzle: performance. Because it's not enough for a system to just work. It has to feel fast. It has to feel responsive, even when it's under an enormous amount of load.
Caching is one of our best tricks for speed. You can think of it as the system's short-term memory. Instead of running all the way back to the main database every single time for a piece of data, the system keeps a copy of frequently used stuff in a super fast, easy-to-reach place. It's a total game changer for performance.
So what happens when 2 people try to edit the exact same thing at the exact same time? We need a way to manage that. Pessimistic locking is cautious. It locks the data first, assuming there's going to be a fight. Optimistic locking is, well, more optimistic. It lets everyone work and only checks for a conflict right at the very end. It's great for high-traffic systems where actual conflicts are pretty rare.
So, as we've seen every single step of the way, from networking to databases to how we scale, it all comes down to balancing competing priorities. It's an art form, really, the art of the trade-off. And this quote just hits the nail on the head. There is no magic bullet. There's no single right answer. The whole point is to understand these core ideas and their trade-offs so that you can make the best, most informed decision for the unique problem you're trying to solve. So I'll leave you with this final thought. What do you value most? Because the answer changes for every single system. For your bank's website, it's got to be consistency. For your favorite online game, it's all about speed. And for a social media feed, maybe it's reliability. And that right there is the art and science of system design.